Welcome, everybody. We are live. Welcome to the stream. We'll let some people file in. I see some people asking, is this thing on? It is on now. Fear not. So welcome, everybody. Today, we're talking more about database internals, chapter 5 of this book here. It's a very good book, and chapter 5 is arguably, potentially one of my favorite chapters. There's a lot of really interesting stuff in here. So we're talking all about database transactions today, and we're going to do hopefully a decent length stream because there's a lot of really interesting stuff. This chapter covers, it's not just like what is a transaction, it covers all the internals, as you might expect, behind transactions. So it covers kind of everything related to that. It covers the buffer cache, which is very related to transactions because they're synchronizing the buffer cache with disk, and how does that impact when you're running lots of transactions on your database. It talks about ACID compliance in general, talk about different kinds of eviction algorithms for that page cache. We talk about different consistency issues and deadlock. And there's a ton of super cool things that this chapter particularly talks about. So I think we can have a nice, long, pretty fun stream today going over all of these cool things. So I'm glad you're here. So hi, hello. Yeah, everyone should file on in. I'm going to pull up and just make sure this is working on all the different places. So let's look here. Yeah, it's working. Let's see. I don't actually see it on Twitch. Why is it? Oh, I don't want to reload that. I don't see the stream up. There we go. It's working. Yeah, cool. Hi, excited for this one. Awesome. Yes, I think this one's going to be fun. Hunter says hello. Let's see, what do we got? Oh yeah, some people should be working now. So if anything's not working, let me know. I'm going to switch over to, let's just look at this here. So this is the thoughts on some of the stuff we're going to talk about today. And like I said, so it's if you are new to this stream, welcome, first of all. But what we've been doing the past couple of weeks is we have been talking about this book, Database Internals by Alex Petrov, and I've been reading it. And as I read a chapter, I'll do a stream and we'll talk about some of the topics. And I often post clips of what I've been talking about on the stream to the YouTube channel. So this is like a super high level overview of what this chapter was about. And there's obviously lots of good details. So if you really want to follow along with this, and just in general, if you want to get good at databases, I think so far, even though I'm only 5 chapters in, this is an incredible book to read and to study for this kind of thing. And, you know, there seems like everybody on the internet, on Twitter, maybe less so on LinkedIn, all people can do seemingly is talk about AI agents and Ralph Wiggum loops. And don't get me wrong, I love all that stuff. But in my opinion, at least for the foreseeable future, learning how to use all the AI tools to accelerate your software development, to build things faster, to automate lots of processes is amazing. But you should still know the fundamentals in order to design and build good systems and to be able to kind of leverage those things to their most effective way. So in my opinion, still reading books and reading papers and studying the fundamentals and studying data structures is still extremely important and extremely valuable. So let's see. Vlad says, hello from Romania. Hello. Thank you for resharing that. I saw you did that yesterday. Hopefully get lots of good discussions in here. George asks, are the previous streams saved somewhere? Yes, they are. Let me just, I'll share the link with everybody in chat for the YouTube channel. So if you would like to look at old streams as well as some clips that I do, and at some point I may start just uploading videos that aren't just clips, but I might just record some videos for the channel. But this is where to go. We also, where did the book go? I set it down somewhere off the desk, but we did streams for designing data intensive applications last year over the course of a couple months. That's a very good book as well. Yeah, so I recommend it. Someone says, hi, I'm from Sri Lanka. Nice. We got people all over the world. Pakistan. Cool. Yeah, we got all kinds of stuff going on today. Sweet. So let's go back to the side-to-side view here. So this is some of the stuff I want to talk about today. I know last time I did a little bit of like AI coding and Cursor, and I'm going to shift gears back to just kind of focusing on some core concepts. One, because I think that's what most of you guys are interested in, but also because there's just so many cool topics to talk about today. But like if the other thing I like about these streams is I do go over these topics, right? So that if you're following along with the book, we have something interesting to read together, look at together, discuss together. But I also like answering questions. So, you know, you can just pop this on in the background. Maybe you're doing some work. Maybe you're just chilling. You know, drop questions in there. I may not get to them right away. I may have to circle back, but I kind of like the interactivity of all of this as well. So should be a fun day today. So let's see, maybe we should start by just talking about ACID, which is kind of a very high level, like it's a good high level place to start for this stream. And then we'll get into some of the details, but that is actually a very good thing to cover to ensure that you kind of know your fundamentals. So let's go down and maybe we'll do a little intro and then we can start doing this more here. So how do we want to intro ACID? Let's see here. ACID is one of the most important frameworks for thinking about relational databases. And this is an acronym that stands for atomicity, consistency, isolation, and durability. And so let's talk about what these four things mean and kind of how they tie into relational databases like Postgres, MySQL, and other popular ones. All right, so let's see. Let's draw boxes to kind of think about these individually here. So we'll first draw our atomicity box right here. So this is the first, and let's actually just define up here. What we're talking about is ACID, and atomicity is the first one that we'll kind of discuss. And what this means is when we have our database and we're doing queries or transactions on our database, we want to be able to think about all of the operations happening in terms of atomic units of change. So this is really simple. Like we could think about just a query like select ID email from, let's see, ID and email from user where ID equals 100. So this is a really simple, you know, SQL query. And this is kind of easy to think about it being atomic. In fact, it almost hardly even matters because this is a query that doesn't modify or change anything about our database. It's just, hey, let's find the identifier and the email from our users table where the ID is 100. And if we think about this, that's fairly simple. We go into our database, we do some kind of lookup in a B tree, in an index to figure out where this user is. We grab the ID and the email, and then we return back, right? But even this, right, this is something where if you think about it, when this query is running, there could be other queries that are running that are making a change to user ID 100. And I don't want to see like partially updated data and partially unupdated data. I want this one query to have a nice isolated view of what's going on in the database, right? So this needs to be an atomic operation, but this gets more interesting when you're doing updates, right? So we'll just kind of use some pseudocode language here, but we'll say like update the table user where ID equals 100, and then let's set email equals to Ben at abcd.com. Something like this, right? So now we're doing an update. And again, this really isn't maybe all that crazy, but it's like, okay, we want to make sure that this operation happens in one atomic unit, right? There's one moment in time before this where any query could see whatever the old email is. And then there's a very distinct point in time where all queries that happen after that will see this new email address. Now, there's an even more sort of interesting part of this, which is when you have transactions that can do multiple queries in them. So you can do in Postgres and in MySQL and a lot of relational databases, you can begin transactions and then either commit them and roll back. So the begin statement often is what commits a transaction. And then within a single transaction, you could do like multiple different statements here. I might need to zoom out a little bit to fit all of this. So let's do another, and let's update user with ID 200 to joe@abcd.com, and then I'll commit down at the bottom. Okay, so now we have something a little different going on here. When I say begin, this begins what's known as a transaction in these databases. And from the moment a transaction begins to whenever it commits, this entire unit of operation needs to also be considered atomic. This is one of the key things about atomicity, because by putting things within a transaction, I'm essentially saying this is one unit of work, even though it might involve like changing multiple values in multiple tables, it all needs to happen like in an all or nothing way, right? Atomic means you can't split it any further, right? So what could happen here is like you could say, okay, I begin this transaction and then I update the user with ID 100 to this email. But then maybe while this is executing, there's another transaction or another query that comes in. Select, let's just say select star from user where ID equals 100. So if this transaction happens like right here in time, but it's from a different connection, what is this user going to see? We actually don't want them to see ben@abcd.com, whatever the new email is, because this hasn't committed. It needs to be all or nothing. And if I allow this transaction at this moment in time to see this, I'm giving it an inconsistent view of the world. Nobody should be able to see this update until after that commit has happened down there. And then this select can start seeing the new email address. So this whole idea of just keeping either individual queries or transactions that have multiple queries in it atomic is a big sort of part of the like complexity of databases, right? And databases, you know, I actually posted on X about this yesterday. There's, again, all this talk about agents being able to implement things and build things very autonomously, which is very cool, but they also have severe limitations. One of the things that I think would be a fun experiment is to just let an AI agent kind of go full ham on like implement Postgres or implement MySQL and to see how far it gets. Because on the one hand, databases can be very easily tested just with like unit tests and text, right? Because they don't have graphical user interfaces or web pages. But on the other hand, they're some of the most complex pieces of software in the entire world, right? Due to all of the concurrency that they have to control and transaction management and storing data safely. So it would be interesting to see how far something like that could get on an extremely high complexity piece of software. But this is kind of the core idea behind atomicity, right? There's all these transactions and queries that can be running, oftentimes many happening simultaneously. That's a part of what modern databases like Postgres and MySQL, you're sometimes running them on servers that have 64 cores or 128 cores, and there's hundreds of connections on a single server, tens or hundreds. And so you need to be able to do lots of things simultaneously while keeping a consistent view of the data. I need to set something here real quick. Yeah, I need to change the AC setting here. All right, so let's go down now. And let's look at the next component here. So we have atomicity. The next thing to talk about is consistency. Now this one, consistency, is one that even the book mentions, and you'll read this in literature, that this one is kind of like the odd man out in this whole ACID framework of thinking about relational databases. And the idea behind consistency is at any given point in time, we should make sure that our database is presenting a consistent view of the world. Whatever you're trying to model with your data, maybe you're a social media platform and you're trying to model all of your users and followers and posts. Maybe you are a app like YouTube, right? And you're trying to model videos and comments and user accounts and view counts. Whatever the database is modeling, it should always give a consistent view of the world that doesn't have data inconsistencies and values that are incorrect or relationships between followers that are impossible to have, right? We should always be consistent. Now, this is partly the database's job, And that's related to things like atomicity, and the database needs to make sure data doesn't get corrupted or data doesn't get changed or modified unexpectedly. So that partly is the job of the database, but that's also partly the job of the engineer and the application developer, because it's possible that the database is working completely correctly, but your application is sending queries to it and telling it, hey, modify the data in this way, in that way, and the other way. That doesn't even make sense. And then it makes your data weird and inconsistent. So databases give you the tools like defining schema and maybe even specifying constraints on your data and being very specific about what values are and aren't allowed. But on the other hand, that's still up to the applications to make sure the data is actually consistent. So that's why they say that this is the odd one out, because it isn't just about database engineering. It's actually about how you interact with the database itself. Let's see. Oh man, we have a special guest on the stream here. We have Sam. I love how consistent these streams are. Man, you don't know how special this is. Sam Lambert's here. Welcome, Sam. Let's see. Vlad says another aspect of atomicity is the ability to roll back changes. Yeah, against the table and index in the buffer pool during rollback. We need to go back to previous consistent state. Yeah. If we have time today, we will talk about the write-ahead log and rollback behavior, because that's super interesting. And that's all about atomicity as well. Not only during normal operations do you need to be able to do that, but if your database crashes in a state where you've written some data and you haven't written others, when it comes back online, can you bring it back to a consistent state? That's super important. Yeah. Okay, we got a bunch of questions, so we'll take a little break here. Let's see. Hope I didn't miss much. Yeah, we've only been going for, 10 minutes, 15 minutes, something like that. Let's see. How do you make a career in the field of databases? Any books or papers you recommend? As far as books or papers, maybe you came into the stream a little bit late, but this is an extremely good book to get started with. That's what we're talking about here today. Designing data-intensive applications is great. I would not say you should build a career in databases just by reading books. You need hands-on experience. You need to build things with databases or even build databases themselves, depending on what you want to do. And if you follow on X or LinkedIn, I often will post about what papers I've been reading as well. So just if you need like inspiration, go ahead and do that. Good afternoon from South Africa. Well, good afternoon, Kasparus. All right, so let's go back to here. Flipping around in the book, go back to where we were at in the book. All right. So the next component here. Is isolation. Let's make another box here. Isolation is at first glance kind of similar to atomicity, but a little bit different. So like I said before, databases can be highly parallel, where you might have 100 different clients or a proxy connected to your database and all wanting to do things at the same time. Some of these are selecting data, some of these are writing data, some of these are doing a combination of both. And in some cases, you have multiple queries running at the same time that will do things that conflict with each other. We could go down and we could look at this, kind of pull isolation down here. And let me grab an example actually from up here. We'll reuse some of this. So isolation is yet another reason why sometimes implementing databases can be very tricky. Oh, I kind of moved over into that region. Okay. So let's think about two things that might be conflicting here. Yeah, actually, I'll just copy and paste this and we can sort of go from there. Okay. So 200 is new 2. We're just kind of making up some numbers here. Okay. So let's pretend that we'll keep it simple, right? For the sake of isolation, we have two parallel connections to our database that are both trying to make updates to a table simultaneously, right? So this over here is, how do I get to my, oh, here we go. Oh, hold on. Whoa, how do I get out of this? What? I'm confused now. How do I get back to just my drawing? Yeah, here we go. Okay. Where is my menu for editing? What happened to it? Oh, here we go. Here we go. Okay. So we've got transaction, we'll say connection 2, and then we've got connection 1. You guys have no idea how hard it is for some reason to spell while you're live streaming. So we've got these 2 connections. Now, as we can see, we're going down, and one of these is doing a transaction where it's trying to update the email of the user with ID 100 and then do 200 and then commit. And this one's kind of doing the reverse. It's trying to update 200, then 100, then commit. And if we think about these 2 things happening simultaneously at the exact same time in a single database server, there's a lot of complexity to figuring out how do you actually handle this. So both of these things are supposed to be atomic. They're not supposed to be affecting the outside world and what other transactions are seeing right until the commit happens. But they're doing things that ultimately, if these try to commit and write to disk at the same time, they're going to conflict with each other. Either, if we're kind of naive about it, one will just overwrite the other, right? Like maybe connection 1 happens to commit 1 microsecond before this one. And so connection 1 writes, and then connection 2 immediately writes and overwrites connection 1's change. That's most likely not what we wanted to happen, because there was a reason why we were doing both of these writes. So there's another way that this could be handled is databases can actually basically keep track of as the transaction is executing, right? So this is executing, and as it's going, it's keeping track of all the changes that it has modified. And this one is tracking that as well. And then by the time it gets to the bottom here, if both of them are committing, or maybe one commits, a millisecond before the other, there's actually a process to figure out, okay, there's some conflicting writes that happened. And so it will only allow one of the transactions to commit, and it will actually purposely just kill the other transaction and send a message back to the client saying, there was a write conflict, we had to kill your transaction, please try again. And so then in your application logic, you have to have retry logic for this. Or there will be deadlock detection, which we can talk about more later, where locks are kept on things. But there's a lot of complexity in making sure that as you're changing things in multiple connections, those things are not conflicting with each other. I'm actually going to pull up, it's just very fitting because, speaking of isolation, I actually recently just wrote an article for PlanetScale on database transactions, but the main focus of it was on how isolation works in Postgres compared to MySQL. So if you want kind of a nice read, but also some interactivity, so we have these kind of interactive scenarios where it will show terminals and kind of show different sessions and how, what happens when you commit versus rollback. I would recommend, a little bit biased, but recommend doing this because put a lot of effort into making this really good. And in addition to that, I actually have some visuals that show not just, queries being run, but actually, in Postgres, for example, let's say we have 2 sessions and they're both doing some reads and some writes. Like, how does this actually work in Postgres, and have similar examples in MySQL, and then eventually get down to even talking about some scenarios of, which we'll talk about today too, things like phantom reads and non-repeatable reads, like showing some of these scenarios interactively and kind of then talking about a little bit how MySQL and Postgres handle these things to avoid problems. So a little plug for that, but if isolation in particular, if that sounds something interesting to you, that's a good place to go to learn more about it. So then we'll get to our last one. Lots of copying and pasting today. Okay. And then finally, the last one is durability. And all of these are extremely important, but of course, let's try this again. Oh, there's a few questions. I'll get to those in a second. So the last one is durability, and this is very important as well as all of the other ones. But of course, in a database, you want to make sure that if you write something, durability, if you write something to your database, it should be durable. A database is really not a very useful database if you can write something to it and then you check again 5 minutes later and it doesn't have the thing that you wrote, right? So ensuring that every time a write happens, that it never gets lost is a, again, whole other aspect of databases that make building and implementing them very complicated. And this actually is at multiple levels. So one level is the idea of durability on a single server. And that's things like, hey, if I have inserted a new row into my table, by the time I get a response back to my client, there should be 100% guarantee that that row has made it onto disk. The way that this works can actually use some tricks like write-ahead logs, where you can actually write that to a log, and then you only update your table and your indexes in memory, and you push those out to disk later on. So there's some tricks to enhance the performance of this, basically. But it still is durable. It has been written to disk. So that's one aspect of durability. And then the other broader aspect is, well, technically, even if on a single server you have perfect durability, there can still be things like a solid state drive can fail or a hard disk drive can fail. So how do we make sure that there's durability in terms of multiple copies of my data sitting on multiple different servers or in multiple different data centers to ensure that even if there's like a sporadic hardware failure or natural disaster or something like that, that I still have my data and I haven't actually lost everything. I'm not depending on like a single piece of hardware to keep my data durable. So there's the micro scale of durability on a single server, which is complicated in itself. And then there's the whole idea of replication, which Postgres and MySQL have different techniques for doing replication built into them. Whoops. So Postgres and MySQL have capabilities for doing replication built in, not really the subject of discussion for today, but a very important part of durability. So those are the 4 cornerstone concepts of relational databases. And there's a lot of complexity to each one and a lot of interesting engineering that goes into each one as well. Let's see, a bunch of comments. Let's go look. Let's go back up to where we left off. Can you make a paper shelf similar to Arpit Biani? I don't know exactly what a paper shelf is. Let's see, you added another comment, but maybe you see you're on YouTube. You can, on either LinkedIn or on X, like DM me and maybe you can explain more what you mean. Let's see, what is the best resource or path to get into Postgres contributor stream if I'm yet to learn C? Yeah, that's a good question. So if you don't know C or C++ at all, it might be a little bit of a long journey to get to the point where you're like an active Postgres contributor. Not saying that it can't happen, but there's a lot to learn, right? Because you need to kind of get the fundamentals of the language, which of course there's lots of tools these days to help speed up that process. But then it's also about like really learning database fundamentals well, and particularly for Postgres, learning Postgres specifics, how different structures work in there. And probably something that would be good if you have a plan to eventually get to that point is, even if you're not ready to start now, right now, you can start paying very close attention to the different email lists and feature proposals and all of the stuff that's going on in the community. Because let's say 1 or 2 or 3, whatever years from now, you want to be a more active contributor. If you're already very well versed in what the active stuff being worked on is, that's going to give you a leg up for sure. Okay, yeah, this was back when I was talking about the 2 transactions, but yeah, so that was an example of deadlock. Some databases would handle that with deadlock like MySQL. Some do more optimistic things, but yeah, ultimately it's an example of deadlock. Let's see. Yeah, unfortunately, I don't know Cassandra all that well. Okay, what can you infer from a scenario where DBMS reports write-ahead log corruption, especially if this occurs when you try to access the same file on disk? Yeah, I mean, if your write-ahead log is corrupt, that's a really, really bad state to be in, right? Because most databases are relying on the wall to be essentially the temporary source of truth until things are flushed to disk. So if that's corrupt, hopefully there's a way to like repair it, but otherwise I'm not actually sure what, you might just, that might be a case where you're risking data loss essentially if you have corrupt wall, which is why the wall is important and you don't want to mess that up. All right, so let's look back at the list, which actually organize some of that stuff that I just did there. Put this over here, and then we have this. Whoa. Yeah, but very good questions. Keep the questions flowing. I like answering the questions as we go through these topics. And for those that came in late, let me just copy and paste this here. Put this in. So if you enjoy these kind of videos, what I would recommend is one, subscribe on YouTube because, and I think you also I think if you want to actually get notified, you have to actually hit the little notification bell, which I know is annoying. But if you want to get notified, I try to post like on Twitter and whatnot, like when I'm going to, with some advance, right, a couple hours in advance or a day in advance. But if you want to get notified, like make sure you're subscribed. But then also, like I said, I post clips. So I know a lot of people can't make an entire stream. You might pop in for 30 minutes and then you got to go somewhere. So what I do is I'll take highlights from the streams on interesting things we talked about and post those to as YouTube clips. So then just throughout the week, you can see what we talked about and follow along. Let's see. So someone asks, are you going to explain how each isolation level implemented on a high level? Well, I mentioned this blog earlier. So if isolation levels interest you, I highly recommend this blog. I wrote it, but I put a lot of time into trying to make it very informative and accurate. So it's not going to teach you like how to actually code it, but if you just need to understand what does Postgres do to maintain isolation between transactions, what does MySQL do, kind of how are their architectural choices different, what are the pros and cons, this is a great thing to read because it does a compare and contrast of basically the two most popular databases in the world. And like I said, I kind of companion that with a couple of nice visuals. So for example, one of the things that Postgres does to maintain this is it uses MVCC, multiple versions of rows. And this is just fundamentally a part of how Postgres's default table storage works. But it also plays into how transaction isolation works and keeping changes isolated from one to another. So I have like a visual example here that shows, hey, let's say I have a session where I'm doing a bunch of updates and over time we're like creating new versions of rows. And then if I do a vacuum, I have to get rid of the old versions of rows and essentially recompact my table, right? And this is on the one hand, kind of a cool feature of Postgres. On the other hand, it can lead to a lot of problems, this idea of having to do all this vacuuming and maintenance. So give this a read if you want to learn more about isolation and how that works. How are atomicity and durability implemented internally in a database? Yeah, we don't, unfortunately, there's so many cool aspects to that we don't have time all in this stream, but a lot of those things are going to be covered right here in this book. So for those who came in late, we're talking about chapter 5 of database internals today, and which covers like transactions and some of the stuff related to that, but we won't get into every detail. Okay, yeah, you've been looking for good examples of MVCC. Well, I would start with this blog because it does talk about it. And then there's other resources that you can dive into, some different papers, or even just the Postgres docs that talk about how Postgres does MVCC. Or again, this book, right? I think this book cost me $40 or something, but so far it has been well worth it, even just for the first 100 or so pages that I've read. All right, so let's go back to the drawing board and figure out what we want to do next. Probably the buffer cache. Yeah, man, there's so many cool things to talk about. We probably won't get to all of these. Oh, where was the blog shared? I didn't send a link. So it's on the Planet Scale blog, but let me get to the link here. Put this. So I'll put that up on the screen too. So that's the blog I'm referring to. All right. Cool. So let's go back. The buffer cache is kind of one of my favorite things to talk about. Because I just really like how it works. It's a very fun thing. And I also have a blog that kind of talks some about that. So maybe we'll jump to that too when we get there. Let me go prep the drawing board for this. I think I'm gonna make this bigger because when we do stuff with B trees, we need a nice big wide space for talking about this. So yeah, we're gonna start with this example, but I'm gonna copy it and we'll go elsewhere to walk through the example. Okay, whoa. So get rid of that and that, all of these. Okay, let's see. So yeah, let's put that over there for now. Okay. All right. I should go up here for the B tree. Yeah, okay. All right, so let's do a little intro. Oh, Zhao says this is an amazing blog. Thank you. Yeah. It took a lot of effort. I know, it's one of those things where the kinds of visuals that I built in database transactions, maybe it's not the most popular thing to talk about because unless you're a database nerd, not everyone cares about the nitty-gritty details of transactions. But if you do, I think it's a really interesting and fun blog. So caching, let's see, how do I want to intro this? The buffer cache in databases is super, super important for getting high performance out of your system. So I want to talk about how it works and how it helps make things faster when fulfilling queries in a SQL database. Let's go down to here. And that positioning is kind of annoying for the video there. Let's scoot the video up to here. Okay. So we'll start by just looking at a B tree, right? In a database like MySQL, table data is in clustered indexes, which means your table data itself is actually in a B tree. In Postgres, it's done a little bit different, where it uses a table or a file with a bunch of pages in it that have your data. And then auxiliary indexes are used even for your primary key and for other indexes that point into this big table file. But we're going to go with the example of having our table data itself be within a B tree. So I have what you might think of as a typical B tree here. The primary key or the keys are going to be the IDs of our row. So in my root node up here, I have like 20 and 40, and then I have an extra empty gap over there. And then I've got, this is a 3-level B tree. So then my second level has a few nodes. And then my third level is down here, and it's just all leaf nodes, right? And it's a really, really simple set of table data. So each row we're saying is just an ID and a name. So extremely basic, just to make it kind of fit on the screen better here. So throughout the process of a database running and doing lookups, right? If I say a query like the following, let's say I want to do select star from user where ID equals, let's do 17 down there. So here's my query. Make this bigger. How is this going to be fulfilled? Well, we're going to find our root node, right? At some point we need our root node. We're going to say, okay, 17, we're going to compare this to the first key. It's less than that. So I'm going to follow this path down. And then we're going to look in here. 8, it's bigger than 8. It's bigger than 15. All right, I need to follow this path down. And then we find our row right there and can read that. So for this, if my database just needed to do reads from disk every single time it needed to do a lookup, it would have had to do a read for this page right here. So that's one. And then once it loads that into RAM, it goes through and it finds the right pointer to follow. And by following this pointer, it would have to then also read this element into memory. So now that's 2 reads. And then we would go down here, and then this one would be 3 reads. But now let's say we do another query. I'll just duplicate this one. We'll put it over here. Make sure it fits up there. Let's change the color to orange. So now I want to look up the user with ID 12 down there. So that's Ian. So for this one, again, now it's a whole separate query. And if we have no in-memory buffering or caching, I would again have to find the root node, read this into memory, do my scan and figure out I need to follow this one. So notice I'm following the same path. I'm going to read this in again. If I want 12, I look at this and I look at this, and then I end up following this path down instead and reading this one in. So I ended up doing 2 different lookups. One of them was on the leaf page with 17. One of them was on the leaf page with 12. But the path to get there actually had 2 overlapping nodes. So if you look at this, it's kind of interesting. It would be kind of a waste for me to go read this one in, read this one in, read this one in, and then throw that all away. And then the next query on this table, I have to go read this in again, read this in again, but then I would be looking up a different node down here, right? So there's got to be a smarter way to not always have to do reads, because even on an SSD, which is pretty fast, reading something from an SSD is still order of magnitude, if not more, maybe multiple orders of magnitude slower than reading something from fast like DDR5 RAM on your server. So one of the ways that we solve this is using an in-memory cache, an in-memory buffer in our memory to save some of these pages and nodes of B trees that are commonly read, so that we can perform these lookups faster and do less I/O on disk, which in turn makes our databases run faster. Let's see. I want to make a copy of this B tree. Oh, but I don't want all the drawing on it. So let's go over here. Move that up, move that here. We'll zoom in on this. Ooh, I'll just move this over to this side. Okay, so I've got the B tree here in a little diagram showing the CPU, which when a query comes into my database, it's going to come to the CPU, right? And the CPU needs to parse the query. It needs to create a query plan, figure out what tables need to be looked up. And from there, then it needs to start doing the I/O to like read in the appropriate pages. So what I'm going to do is I'll actually take this B tree here, and we're going to bring it in, and it's going to look a little bit awkward, right? But really on disk, this B tree it's not formatted, like it doesn't literally look like a tree. It just looks like a bunch of pages that have pointers to each other. But to keep things simple, I will just take this and we'll kind of put it in this SSD box to represent, like, this is what's on disk. Let's see, maybe it would be better to structure this vertically. Yeah, so I'm going to take this, do this here, and then I'm going to take this will be better. Structure this vertically for the screen. Take the CPU up here. Okay. This is my page cache. This is my CPU. And then do this here. Okay. That's nicer. All right. So the CPU, right? A query comes into the CPU. I'm going to find my example query that I had from earlier. Where was that? Yeah, it's this one over here. All right, so a query comes in on the CPU. Let's say select star from users where ID is greater than 20, less than 40. So this is a scan, and we want to do some ordering. So once the CPU has parsed that, we need to start doing IOs. And what would we be doing for this? Well, we would want to look at, first we need to get the root node of the B tree. So we're for sure going to have to load this in. So I'm going to do an IO to bring this in. But what I'm going to do is when I do that IO, I'm actually going to keep this page in my page cache, which this is RAM. So this is a chunk of RAM that has been specified as storage space for pages from your B tree. And then I'm going to mark this as, okay, it's in the cache. And then on disk, just going to color coordinate so that I know this is one that is in cache. So then the next time, like if this select is running, but then 10 seconds later, another select comes in on this same table and it needs to start at the root node to do a search, it doesn't even have to go to disk. I already have a copy of it in RAM, and that's much faster. So I can just do that lookup. Okay, so then for this one, right, ID greater than 20. Well, so we know we're not going to have to go down this path over here. Use orange because those ones are all less than 20, but I'm going to have to go down this path. And these ones are all greater than 40. So I know I'm only going to have to go down this path for this query. So again, I'm going to read this in, but I also know that I'm going to read it in. I'm going to put it in my memory, my RAM, and then I'm going to mark that one as, hey, I also have a copy of this in RAM. So the next time I need to query this one, I don't have to do this slow lookup, which, doing something from SSD. These are using some ballpark figures, but that might be like 10 microseconds. My numbers might be a little bit off there, whereas a RAM lookup is probably in the hundreds of nanoseconds, right? So 1 or 2 orders of magnitude, 10 times faster, 100 times faster doing this lookup. Okay, and so then to actually do the search, we'll just kind of skip ahead here. From between 20 and 40, I'm eventually going to have to read in this one. Oh, wait, I wanted orange here. I'm going to need to read in Tim, Cam, Win, Jim, and I guess none over there. So it's like these 4 rows, which are in 3 different pages. Okay, so this is where things start to get interesting. I will make this page cache for the sake of simplicity. It can only fit 3 pages. So we've got 1, 2, and there's room for 1 more. Okay, so we'll do our first read, which is this one right here. We're reading this for our query. I put it right there. I color code it green. So now that's in there. And again, if immediately after that, someone else needed to look up Tim, it would be there. But now for this next one, I need to move on to this row right here. And my RAM is full, right? And this happens all the time in databases. You might fill up, you might have a 1 terabyte database, and you have 64 gigabytes of RAM that you've specified as your page cache, right? This is assuming a big server with a lot of RAM, but still 64 gigabytes, or if your whole server has 64 gigs, you might only use 50 of those for your page cache. So 50 gigs is 1/20th the size of your full 1 terabyte database. So there is, depending on the workloads, going to be times where you've filled up your whole page cache with pages to do fast lookups, but you'll sometimes have to make a choice and say, my page cache is full, but I need to load something new into the page cache. So you have to decide what to evict. And there's lots of different eviction strategies, which I'll talk about a little bit later. But in this case, we'll do something very simple. We'll say, well, the root node, I'm probably pretty much for sure going to need again. And this one is a part of my scan that I might need to look at again. So I'm actually going to go ahead and evict Tim. So the nice thing is, because I haven't modified Tim, this is easy. I don't have to rewrite it to disk or anything. I'm just going to evict it. Boom, it's gone. But now I'm saying, hey, that one doesn't exist there anymore. And now I'm going to bring this in. So that one's in my cache, right? And so then the same process repeats. We read those 2 rows, but then I need this one. So I'm going to copy this. This one gets evicted. This one goes in here. This one is now my one that's in RAM. But essentially, I have this mapping where subsets of my full data are in RAM, and there's this whole component called the buffer pool in MySQL is what it's called. I believe it's I forget, I think page cache is not the right word. I'm blanking on the correct name for Postgres, but there's a similar mechanism in Postgres, but there's a subsystem of databases whose whole job it is to essentially manage this mapping between, I want to keep as many pages from disk as possible in RAM because it keeps things fast, but I can't fit everything in there. So how do I decide which things get kicked out when I need to replace something? Or let's look at one other example here, which is, let's say instead of doing this select, move that off to the side. Let's see, I'll move it up here. Go back down. Oops, okay. So let's do the following. So now let's say I had just run that previous query. Let me actually bring it back because I want to remember what it was for my example here. So if I just ran that query, but now I'm going to run a different query called, let's see, update user, let's see, set name equals John, where ID equals 37. Okay, so we're going to update this user. So I have this in RAM, and there's a whole side of this with the write-ahead log as well, which I'm kind of ignoring for now. So we're going to simplify things. But I want to update this, which is one of my pages in memory, from Jim to John. And what I'm actually going to do in this case, and this is a trick a lot of databases use, is they will write a record to their log so that something is persisted to disk. So in the log, they'll say, hey, I updated row ID 37's name from Jim to John. So there's something persisted to disk. But then in terms of the actual B tree structure, all it will do is update this to John, and then we will mark it red, but this indicates this is a dirty page, which means that if I then go to evict this at some point, I can't just throw it out and put something new in there. I have to actually write this change to disk to make sure that the structure on disk is persisted before I can replace it with something new. So then if I come in with yet another select, and let's just do a select star from user where name equals, or let's just do ID, where ID equals 45, right, which is down on this path here, I will actually eventually have to evict multiple things, because I would go down here and I would say, okay, I'm looking at this node for the beginning of the search. Great, that's already in there. But now I have to go down this path because the ID is 45. So I have to decide something to evict. So let's say I decide to evict John. I have to make sure this goes down here and I update this page. So I'll just type it in here, JON. And again, this might seem simple, but it's costly because writes in databases take a lot more time than just reading and writing from RAM. So now that update is persisted. So now I can get rid of this, get that out of there. And then I will bring in this page into my page cache because I'm following down this way for my search. So now that is in there and this no longer is. So I no longer have any leaf nodes in my page cache. It's just internal nodes. And then I would know that I have to go down here and I have to evict something. And again, there's different algorithms for choosing what you evict, but because this is the more recent search path, I'm going to choose to evict this one this time. There's no updates to it, so I don't have to write it to disk, but now that's not in there. And I'm going to make a copy of this and bring this into my page cache, and then I keep that in sync. So that actually really only scratches the surface because there's a lot to this, right? We came up with some very simple examples, but you have to consider many queries can be executing on this same table, doing lookups at the same time, right? Concurrency. What happens if while all of these transactions are happening, you might do insertions, which then trickles up to, well, I have to split an inner node, and it might even go so far up as having to split the root node. And how do you invalidate your cache when you actually have to do splits in your memory and making that sync with disk at the appropriate time? How this interplays with the log that I mentioned, which we haven't talked about much. And then again, the algorithms for actually choosing, right? There's better and worse algorithms. They're not all created equal for how you choose to evict something from RAM, because ideally you'd never want to evict something where 1 millisecond later you're just going to need to pull that same thing back into RAM. You always want to try to make the best choice for, I want to evict the thing that I won't need for the longest amount of time, but doing that perfectly is hard to do while you're also doing it efficiently time-wise. So this is really a fascinating area of databases. This only kind of scratches the surface, but gives you a good idea about how these things work in databases, and why we need a page cache is because the reads and writes that we do to here happen order of magnitude or multiple orders of magnitude faster than reads and writes even from a solid state disk. So there we go. Oh, shared buffer in Postgres. Yeah. Someone corrected my terminology there. Let's see. So yeah. Hooray for DB nerds. Yes. Hooray for database nerds. Oh yeah. So did Vlad ask what the drawing tool was? Yeah. If someone asks what this drawing tool is, it's Excalidraw. It's a pretty good drawing tool. This is something that if any of you watch Theo's streams, he uses this a lot to explain usually, like, whatever topic he's talking about. But yeah, it's a good tool. I've also heard great things about TL Draw, but I just have less experience with it, so I've stuck with this. I'll also say I like, it's not necessarily the greatest for live stream stuff, but if you're doing, if you want to do very stylized, like ASCII type diagrams, this tool, MonoDraw, is very good for that kind of stuff. I really like this tool for that. So anyway, but not really the greatest for live streams. I tried that before. Let's see here. Will this be recorded? Yeah, so this is going to go on the YouTube. Yeah, so some people are asking from LinkedIn. I know it seems annoying, but I'll drop the comment again. So the streams are available on YouTube, and you can also subscribe to the channel for, if you want to get more updates, like when new videos drop or when I clip a video, subscribe and set your notifications the correct way. Let's see, is star recommended only when you use limits? Thanks. Oh, okay. So you're probably talking about like select star from user. Star just is select all columns. So if you don't need all columns, you maybe shouldn't be doing star. Like if you have a database with, where the table has 100 columns on it and you only need 3 of those columns, you shouldn't use star. You should just select the data that you need, because that will, at the very least, reduce bandwidth, because less data will have to be egressed back to your app server. So yeah, generally like use star if you need either all or most of the rows, but don't use it if you only need a few. Let's see. Oh, big can of worms here. In Postgres, what's the best auto increment? Yeah, so serial, like sequences, there's UUIDs. Yeah, so there's lots of debate about what the best kind of primary key is for a database. A good kind of nice, safe starting point is to use some sort of big integer that is auto incrementing. So like in MySQL, this would be a big int, and you set it to auto increment. And it's a nice, increasing value. And if you use big int, that's a 64-bit number. So you should never run out of those identifiers. There is some argument for UUID, especially since UUID 7 is becoming more commonplace. Some versions of UUID are not that great. There's nano IDs. Yeah, there's a bunch of debate on that. Probably won't get into it all here. But yeah, it's some good stuff there. There's a lot of like blogs and articles about it. What is the difference between a page table and page directories? Not exactly sure. Maybe someone else can answer that question. Maybe there's some terminology with page that I don't quite understand. Okay, so how are you liking this? Was this example useful? Hopefully it's useful. Put that over here. We'll go back to our list. The list. So here's what I wanted to talk about today. And again, I figured we wouldn't get to all of this. Can probably only do like 2 more of these topics. But I am having fun hanging out. Okay, let's do this question before we move on. UUIDs are not safe, right? Depends. So there's a few potential problems with UUIDs. I know I keep plugging PlanetScale, but there is legitimately a very good blog. Let's look here. Problem with UUIDs is a primary key. So this is focused more on MySQL. Things are a little different in Postgres. And shout out to Brian, did a great job with this article. But there's lots of different versions of UUID. There's UUID v1 all the way up through v7, and they all have slight differences in basically the ordering of bytes, right? Which chunks of bytes come in which order, which impacts the overall, are your UUIDs like increasing sort of monotonically, or are they random, which can impact how things are laid out on disk, depending on whether you're using MySQL or Postgres. And then there's also like, it's an extremely low risk, but there is potential risk of collisions. So basically the answer is it depends on which database system you're using, which version of UUID you're using. It might be overkill, it might be fine. But I'd recommend giving this article a read because it gives you a nice overview. And then based on your database, you can make the right decision. I saw your GitHub and saw you do a lot of JavaScript. Yeah, I like, I've never like been a professional front end dev. Like I've never been hired to do that full time, but I do like, building apps. That's one of the reasons why I make those blogs that have the interactive components, because I think it's fun to augment written text for education with some form of interactivity. So yeah, I like a mix of both. Maybe the combo is unusual. I gotta go back, I guess. Wait, here, yeah. All right. So I wonder what we should look at next here. Let's look at, we'll do, I had an idea to talk about the basics of some eviction algorithms. So I'm going to paste this here. I'll do a little bit of organization. Oops, I don't want to move that. We'll move these right there. I'm going to move this stuff up. I'm going to move this over here. Okay. Sweet. Move these a little closer. Put the CPU down there. Okay, cool. So yeah, I think what we'll do next is talk about eviction algorithms. Oh, could you please post a link to the article on YouTube? Just Google PlanetScale UUID blog. If you Google that, it should be the first result. PlanetScale UUID blog. All right. Cool. So let me look at, where do I want to go here? I'm just going to check in the book where it's talking about, some of the different eviction algorithms. Okay. Let me take this comment off. How do I remove the comment? Okay. So let's see where to start here. Eviction algo, how to hack the tenancy system as a landlord. Nice. The eviction algorithm that you choose for your cache is really important has a huge impact on how well that cache performs and actually helps your database or other data systems. So let's go through some of the different algorithms that can be used for this. Now, we'll start by looking at a similar but a little different picture from before. Actually, let's change that here. We've got a little setup of a basic caching system. So I've got my data pages on disk. I've got a CPU that's making requests to RAM, which is acting as my cache. And then I've got data in that cache. So this is just looking at kind of how it works for a local system, right? Caching pages from disk, which could be a database system. This also could just be like general pages from a file system. But caching also works at like a broader scale. You can actually have database servers running Postgres, MySQL, and then you could have like a Redis or some similar kind of caching service that are separate servers that will cache results. And you can either fetch things from cache or fetch things from the database. So the principles we're talking about here, these algorithms, are really very generally applicable to caches broadly, right? But what we're looking at right here is I've got a cache that's already full. And basically the way that this setup is my cache size is about half the size of my data that I can store on disk, right? I've got 8 pages on disk. These are database pages, right? So each page has 2 rows of a very simple table with ID, name, and email. And then as my CPU needs to request data, it puts things in the page cache. So there's a few different algorithms that we can use for this. One kind of very basic algorithm, I want to get my list over here. So I'm going to just want to copy this list so we can look at it very easily and reference it while we're going here. So there's several different algorithms, right? First in, first out, FIFO, LIFO, last in, first out, LRU, clock, and there's also some more sophisticated ones. But we'll start with something very simple, first in, first out, which is the following. We'll kind of walk this through from the beginning here. So we'll say a blue page is one that's not in cache. So let's say the CPU requests this page here, right? So I make a copy, I put it in my cache, I make it green. Great. We'll repeat this process a few more times. So now I want to read in this one. So that's going to go in here. We'll make that green. And notice how this kind of got pushed down because there's still room. Okay, now I want another one. We'll grab this one, make it green. And then finally this one, we'll make it green, make a copy. We push these down. Okay. So now I've made some requests. I've gotten to the point where my cache is full. Now there's another request that comes in, and let's say I need this page. So I have to make a decision. What do I evict? Now, using what we were talking about over here, I need to move a little bit, so you can see. So using what we were talking about, first in, first out, means the first thing that came in previously is going to be the first one to go out. So everything I have right here, you can essentially think of this as a list because I was bumping things down, which in RAM, you wouldn't actually copy everything around every time. But this was the first one that came in. So when I need to make room for something new like this, I'm going to evict this page, boom. And then I'm going to make sure it's labeled appropriately over here. It goes back to blue. But now this one turns green and it's going to go in here. And just for visual clarity, we'll actually like shift everything down and put this in here. And so now that goes in there. And then again, let's say I now need this page. Well, this one of everything that's in the cache currently was the first one that was read in. So this gets gone, this gets reset, and then I'm going to do this and make a copy of it and put it into my page cache, right? So we can see first in, first out. It makes sense. It's pretty self-explanatory. This generally is probably not what you want to do. So if we think about the case of a database, and I guess it does depend on your workload, but for a database from prior, right, the one that is first read in, so like I think it was this one that I had on top at the beginning, right? Most likely, the early on, like your database boots up and it starts fulfilling queries, some of the first pages that are going to get read into your cache are probably some of the most important ones. They're like root nodes for B trees, or maybe nodes that are on the second level of your B tree. And those are ones that are going to get used a lot, right? Because every time you look something up in a B-tree index, you always need to look at the beginning. And if there's a table that's getting 10,000 queries per second, you're probably going to look at that B tree, potentially that root node, 10,000 times every single second. So it would be silly to be like, hey, I need to load some row in that I'm not even going to use that much. I'll kick out the first thing that came into RAM, which is my B tree root, and then it will just have to get loaded in a millisecond later, right? Which is silly. So generally for Postgres, MySQL, and really just like most cases, first in, first out is too basic. It's too rudimentary to work well. So then we'll reset the colors here. Last in, first out is a little bit different. So actually, let's go back. We'll start rather than kind of, let's see. Yeah. I just want to make it a little bit more efficient here. So let's say, I'll leave the color scheme over here. Let's say this one was added in, and then it gets shifted down. And this one was added in, right? And then we shift these down. And this one was added in, and then we'll shift those down. And this one gets added in, okay? So similar thing, right? We have some of our data in cache, and now I decide I want to bring this one into the cache. Let's make it a different color. How do I decide what to kick out? For last in, first out, it's the flip, right? The last thing that came in is going to be the first one to get kicked out. And this one probably for databases is going to be better than the alternative, because I'm going to kick out the thing that I most recently brought into my database, which is this one here. And if you think about it, this should pretty much rarely be things like a root node of a B tree or some other like really, really important page, because most likely the thing that was recently brought in was just some random leaf page for a query that was done to look up a user's email, right? So it's probably safer in terms of performance to bump that one out. We put this one in here and we put it like that, right? So this is better in some ways, but then the problem is, realistically, our page caches are much bigger than this. They don't just hold 4 pages. They might hold thousands or tens of thousands or hundreds of thousands. So the problem is there's probably some pages that are down here that came in very early that are really important, but also some that, again, are just, we needed to look up some row and it hasn't been used in a while, but it's taking up a spot, and it just happened to get into my cache really early when my database first started up. And so that one might never get evicted, or would take a very long time for it to get evicted, even though it's not getting used very much. So again, maybe a little bit of improvement, but also still some downside here. And then let's get to now LRU. This is the one that is, I need to update the color coding here. LRU is where we really get a big upgrade. Still not perfect, but generally much better. So LRU stands for the least recently used, which makes a bunch of sense, right? If I have, in my simple case here, 4 pages, but I could have tens of thousands of these, it makes sense to say, hey, I'm going to kick out whichever thing it's been the longest since it's been used, because this is not just relying on the order that things came in. It's relying on how frequently I'm using them, which roughly correlates to the IO benefit that it's giving me by sitting in RAM. A root node, or maybe even a second level node of a B tree on a table that's looked up a lot, probably will be getting referenced a lot. And so we want to keep those there. So let's say this is the state that we have, and I'll just draw a couple of things. So this is the state that we have right now. And then another query comes in, and let's actually make this explicit. I'll add some labels to this. More recent at the bottom. So ones at the bottom are the more recently used ones, and the ones at the top are less recently. So we're going to visualize this as, we're visualizing this by just like using sort of the position height-wise to be more or less recently. What you could use in memory is you would actually use some kind of queue data structure where you don't have to copy things around, but you can kind of keep pointers to things almost like a linked list. There's different ways of doing it implementation-wise. So now we come in, and let's say this is least recently used, and it was about to be the thing that got kicked out, but it gets looked up again all of a sudden, right, by a query that comes in. So it's already in my cache, but I'm just going to change the priority to say, well, that got used really recently. So now that gets bumped up to the most recently used thing. And then let's say Another query comes in that selects 20, Ron. Okay, so now that is the most recently used thing. So it gets bumped in this queue, linked list type structure that we have. So we are keeping things ordered where we know that once I get a query that comes in for this row, and okay, that's not in cache, so I need to make sure it gets into cache. I'm going to take out the thing 5 red that has been the longest since any of my queries in my database is needed. That one goes back to blue, and this one goes in here, and it actually goes in as the most recently used thing. So everything else is slightly less recently used now, and we have this order, right? So this is the basics of LRU, and there's lots of ways to kind of modify LRU and tweak it to work slightly better. But this is one that, whether it's literal LRU or sort of an improvement on LRU, generally is like really, really good for database performance, because it makes sense that you're going to want to keep things in memory that are used more frequently and kick things out that have not been used in a while. It's still not perfect, because it could be that the thing you're about to kick out is going to be needed again very soon. And this is actually, there's an idea talked about in the book that is not just based on how frequently the thing was being used, but how often it is being used. And in that case, you might say, like, just because this thing was the most frequently used, sure, it was frequently used, but it was just one query that used it. And this one right here might not have been used in a while, but once it was read in, it's been read 500 times in the past minute. And so even though it's not the most recently read thing, we actually might want to weight this where it has higher priority to stay in my cache versus the other thing. So that's like yet another tweak and improvement you could make. And then finally, there's this clock sweep algorithm, which the book has a very nice diagram for. Maybe we'll, let's just go and look at, I didn't like build a nice diagram in here. Page replacement. Let's see. I wonder if this has, yeah, so the clock algorithm. Doesn't really have a nice diagram here. Yeah. Okay. Well, I don't have a nice picture for it. There probably is something on here. Let's see. I feel like this is like the most obvious concept in the world for someone to have a good diagram for. Man, that's crazy. Maybe I need to be the one to make the diagram for it. Not shopping. No. Images. Okay, yeah. So the book has a diagram kind of like this. But essentially what you do in a clock sweep algorithm is you have your whole set of pages that are in your cache, right? We had just 4, but however many. And you can set it up in different ways, but you can have like one dedicated background process, which is continually just going around. Like, we think of it, even though it's like a sequence of memory, we can think of it as a sort of circular buffer. And it's basically just continuously going around the circular buffer of all the pages, looking at, is this currently being referenced? If it is, okay, we can't kick this out, obviously. But if it's not currently being referenced by any query, let's tag it as this is able to be evicted. And then when I come around the entire buffer and I get to that again, and it's still listed as this is able to be evicted, then I'll go ahead and evict it, because clearly in the amount of time it took me to go around the whole buffer, it hadn't been used. Or I won't go ahead and evict it, but next time I need something, I will jump to this and use this as an eviction candidate. So you have this algorithm where it can be, again, happening in the background. It could be something where you increment the clock a little bit every single time you do a query to like advance and scan some rows. But you're just essentially doing these continuous scans around the clock and tagging, okay, this hasn't been used in a while, so let's evict it. This hasn't been used in a while. And the nice thing about this is you don't necessarily have to maintain any sort of like queue linked list type structure, right? Which there's some overhead in like maintaining pointers to or if something gets used, we're moving its position in the queue or in the linked list. Whereas this is, you can just kind of basically have a big array of pages with a little bit of metadata on each one for if it's currently being referenced and if it's able to be evicted or if it's reference count. and then just do some maintenance on that in this circular pattern. So this is another one that can be used. So there's a lot to these different algorithms, and as you can probably tell, which one you choose has a big impact on how the caching, how the database is going to perform in the real world. So it's good to choose the algorithm wisely and choose it very specifically based on the workload that it is powering. So there we go. Let's see, some comments. Yeah. It's cool that Vlad is in here. Yeah, answering some questions. That's nice. Yeah, and any of you too, if you are someone who knows databases well or system stuff well, like obviously you can ask questions too, but you can also answer other people's questions, which is awesome. Yeah, so a couple of chats going on in here. Hi, Ben. What's your take on compute storage disaggregation? So I'm assuming by that you mean the sort of the popular idea of separation of storage and compute. And basically, there's pros and cons, right? The clear pro of separating your CPU and your RAM and like the server itself from the drive where things are being stored on is there's a few. One is it's usually easier to scale up and down that separate storage, or more so up, right? Because if it's a separate, distinct, rack of hard drives that is being connected to over a network, you can more easily like add and scale that out. There's also the potential advantage of if that disaggregated storage has its own management for making multiple copies and stuff, potentially data is, you don't have to worry as much about like the manual replication process. So there's some advantages for sure. And usually the disadvantages boil down to performance because you're introducing more latency by separating your storage from your compute. And so you've gained flexibility by disaggregating, but you have done that at the cost of some performance. And that's basically, technology has gotten very good. The separation of storage and compute, like the overhead of that latency you're adding has been like greatly reduced over the years by like making networks and switches and these kinds of things better, which is cool. But physics is physics. You're still always going to have some added latency by doing that. And then also potentially not just latency, but variation, because even though 99% of the time the network might be behaving perfectly, there can be anomalies where the network starts behaving poorly, and then that all of a sudden will add this aspect of unpredictable performance to the database. So, yeah, and I work at PlanetScale, where we do cloud-hosted databases, and we give customers the option of both. PlanetScale Metal is local disks where we're still replicating to other servers, but the disks themselves that are being used are local. So your data is perfectly safe, but you get that ultra high performance IO. And then we also give people the option for that greater flexibility of using a network attached storage like EBS or GP on Google, stuff like that. So yeah. Let's go back to our list. Probably pick one more thing on here. Is this your real background or image? Thank you. Yeah, this is my real background. All right, let's look at our list yet again. So I think what I'm going to do is I think we'll actually talk about Deadlock. The write-ahead log is super interesting and super important. And, maybe there will be another chapter in this book that revisits it again or something. I'm not sure. But it would be cool to talk about Deadlock because there's some kind of fun things. I think it'd be fun to talk about dining philosophers as well. So I'm going to grab a few things to prep the example. Let's see what I was going to do. Oh yeah, we'll do, because this has to do with isolation. So I'll grab this and put that here. And then we'll draw some diagrams along with it. I'm trying to think of what else. You know what we might need? Hold on. I want a good, we'll just jump into it and then I'll cut things out later. Okay. Good content. I approve of this content. As I said before, in university, they don't teach this stuff. Yeah. So I took some database courses in university, and the interesting thing is, I'm sure they're all different, but at least the undergraduate one I took was very focused on theory, which some things was good, how to design schema and things like that. Obviously some SQL stuff and building apps, but also a lot of relational algebra and tuple relational calculus and very math and theory heavy, which is kind of a good core understanding, but really not very practically useful. And so I think it's very good to just focus on the more practical, useful aspects of it. All right. So let's do an intro and then we'll look at Deadlock. One of the things that can happen in a database is, let's think about a better way to say this. Deadlock is a dangerous thing that can happen to the transactions that are running in your database. And databases need ways to detect or avoid these kinds of scenarios. And so I want to talk through an example and some different ways and concepts for dealing with deadlock in software. So the example we're going to look at is, let's say we have two connections to a database and they're both going to try to run transactions. Particularly, let's look at this. So we've got our connection one. It's going to begin a transaction. It's going to try to update the user with ID 1 to a new email, and then also 2, and then commit. Now, at the exact same time as this, there's going to be another connection that's going to begin, and it's first going to try to update ID 200. Notice that that matches over there, and ID 100, which that matches over there, but kind of in a different order. And then that's going to attempt to a commit. So one of the things that will often happen in database systems that are doing this is, depending on which system, but in something like MySQL, they'll grab a lock when a transaction needs to write a database. And a lock is, you can grab locks on rows of data that basically says, hey, if I own this lock, it means I need to do something to this row, and nobody else should be able to have access to this row while my transaction is running. And that would be the case here, because if you're going to change the email during a transaction, nobody else should also be able to muck around with emails. So what would happen, again, running exactly simultaneously, they would both begin. Great. This is going to go ahead and obtain a lock. I'll just draw a little lock symbol here on the ID 100 row. So now, once it has done that, no other transaction, no other query can try to modify this until the commit happens. Simultaneously, over here, this transaction is getting a lock on 200. So now nobody else can touch 200 until it's ready to commit. But then these two both proceed down here and try to make updates on the rows that the other transactions have. So this is going to say, hey, I want to update the email here, but I have to wait, right? These locks are things where it's a piece of software that actually protects this data from being modified until the commit. So now it has to wait for this lock to be released. And this one over here is now in a situation where it's waiting for this lock to be released. This is a deadlock because these both are holding a lock on these rows and they cannot release that lock until they commit. but they are also waiting on each other's locks to be released before they can commit. So this is what the term deadlock is called. And there's a diagram that we can draw for this that goes along with this scenario. I'll just get rid of this, move these up so we can see this scenario a little better. So we'll call this, let's see, connection 1. Right here. Why is that font so large? Doesn't need to be that big. Make it smaller, make this smaller here. Okay. So connection 1 and connection 2, they both have locks on rows, where this one has obtained this lock. But now what we're going to say is connection 2 is waiting on, oh man, why is this drawing not working very well? Connection 2 is waiting on connection 1 to release a lock, while simultaneously connection 1 is waiting on connection 2 to release a lock. So there is a circular dependency here, right? Connection 1 holds a lock that connection 2 is waiting on it to release, and it can't make progress till then, and connection 1 is also waiting on connection 2, right? So there's different ways that databases can choose to handle this situation. What some databases do, like MySQL, is it allows for these locks to be created as time is going on. There's like within MySQL, there's actually a difference between also a S lock, which is a shared lock, and an X lock, which is an exclusive lock. An exclusive lock, which is what we're talking about here, means once I've grabbed a lock on a row as a transaction, I'm the only one that can modify that row or use that row until it's committed. Shared locks are often allowed for reading. So you might have 10 transactions that all just need to read, you know, ben@abcd.com, that email address, assuming that's what's in the database. And it's fine for many transactions to read that data at the same time. But once you get to writing, you need an exclusive lock. So MySQL allows that. And what it actually does is it has a mechanism where it essentially keeps track of these graphs of dependencies within queries. Like there's actual logic in MySQL to do that. This is just a picture, but it's tracking all of this kind of state in code. And whenever it detects a cycle in the pattern of locking that's going on with all of the simultaneous transactions, it actually, in order to make progress, it just forcibly kills one of the connections or one of the transactions. Because the moment that, let's say I kill connection 2, right, if that's killed, now as a part of getting rid of that, why won't it let me select this here? This lock, that's annoying, is now released. It's no longer holding that lock anymore. And then it's also not waiting on this lock anymore. So now this update can go ahead and proceed, it can commit, and then we can move on, right? Postgres does things slightly differently, but it still needs the ability to, it's similar to MySQL in that it still needs to be able to delete these kinds of things. But it's different in how it gets to that point. Let me clean this up a little bit. I wish I hadn't done dotted lines here because now it's going to be very painful to try to get these things. Let me just select all those. Delete, zoom in. All right. So in Postgres, the way that works is a little bit different. What we do is the steps we're going to make very similar, right? So begin. This one modifies this row. The way that Postgres tracks this is it uses predicate locks, which is essentially just a way of, rather than actually restricting access to the rows that one transaction has done, it's basically just tracking what are the predicates, the conditions that this row has made modifications or writes to. So it would track, hey, the condition of ID equals 100, I have a lock on that because I have made changes to that set of data, which in this case is just one row. And then similarly over here, this would track that predicate I have made a modification on. So then once we get down to this point here, And actually, the other thing to point out is in Postgres, when modifications are made, it actually makes a new version of that row. So there's whole isolated versions that get made. So when we get down to here, this would want to be made. But what we would see is when it tries to make this, it would say, hey, connection 2 has already made writes, not yet committed, but it's trying to write to this predicate. And this is trying to write to this predicate at the same time. So it's going to optimistically allow these things to happen. And I actually don't know the details of if it's going to do the killing of one of these at this stage, or if it waits all the way till commit. It might actually allow it to proceed all the way down to the commits. But then once one of them commits, it will say, okay, this one's trying to commit now. I've done all these writes, but I see that this actually conflicts with something that another transaction is doing. So it will let one of these commit, and then the other one, it will say, let's say this one, maybe it won't let commit. It'll say, hey, I detected that you tried to do something that conflicted with another transaction. Sorry, I just chose to have you be the one that has to get killed. So you're going to go away, and you have to reply back to your client that you did not complete your task. And then those new versions of the rows will end up just not getting used. And these new versions of the rows over here are what will actually get applied to the database. So similar, right? We're killing transactions in order to make like the other ones actually work, but the way in which we track it all is a little bit different. Now, there's an interesting related concept to this called dining philosophers, which I think is pretty fun. So I'm going to go grab a picture, and we'll actually bring it into Excalidraw. So I'll just grab, I was on Wikipedia earlier. There's a picture here. So is this a good resolution? Yeah. Do this. And I'll hide the screen for a second. Let me go, where do I do that here? Yeah, let me just get this put into our Excalidraw. Oh, it's over in downloads. There. Where am I? Okay, yeah, I'll go down here. Cool. All right, let's go. Where do I want to be? Okay. Actually, this is one. I might be able to go over to my side-to-side view here. New view that I'm trying out. Oh, man, why is this so difficult to work with sometimes, man? All right, so here we go. Nice, okay. Dining philosophers is an interesting generalization of this deadlock problem and a way of thinking about how you can arrive at a solution. So this is sort of a famous, classic, abstract computer science problem. And the setup for it is the following. So it's called dining philosophers because the idea is you have some number of philosophers. This example picture shows 5, but it's not limited to 5, right? 1, 2, 3, 4, 5 philosophers. They each have a plate and they're trying to eat some special spaghetti, but there's also 1 fork in between each philosopher. So if there's 5 philosophers, there's 5 forks. If there's 10 philosophers, there's 10 forks at a circular table. And the rule is each philosopher can only eat spaghetti if they have both a fork in their left and right hand, right? So there's not enough inherently for every philosopher to eat at the same time. And this is kind of, even though it sounds like a silly example, this is analogous to in computer systems. Each of these philosophers you can think of as one process or one application or one server, one unit of compute that can do some amount of work. And there's a limited number of resources, right? For a given row, there is that row, and we might have multiple things competing for that same row. We could also think about these as just RAM resources, right? There's a finite amount of RAM, and there's all these processes that want to use the RAM. So in our case, these philosophers here, I'm going to undo that. My philosophers are the transactions, right? These are like different transactions that are running on the database. And so the challenge is basically, how do you come up with an algorithm that eliminate starvation, which starvation sounds like we're talking about spaghetti here, but that's actually also a CS term, which is we never want a transaction or a process to never make forward process, to be starved of the resources that it needs, like the database rows or the RAM in cache. We never want to completely starve it out. So there's a lot of kind of fun exercises you can think about for like, how do we make this work? Because there's some algorithms that you could come up with where you would actually get into a point of deadlock on the dining philosopher. So we could think about one algorithm, which is at the start, every philosopher, the first step is pick up your left fork, and then if it's available, and then if it's the right fork is available, pick up your right fork, and then eat for 5 minutes, and then put down your left fork, and then put down your right fork, and then pause for 5 minutes so that you can share with the philosopher next to you, right? On the surface, that seems like an algorithm that would work and that would let everybody eat. But there's a problem, right? Okay, so the first philosopher are basically simultaneously, right? These are simultaneous threads, simultaneous transactions. So this one is going to pick up the fork to the left. This philosopher is going to pick that fork up. This philosopher is going to pick that one up, and so on. And again, this is analogous to transactions taking locks on rows or using different resources. So now their instructions are, the next step is pick up my right fork. And that's the only thing. I didn't say a conditional or anything like that. The moment any of these philosophers go to then pick up their right fork, now all of them are going to be stuck waiting on another philosopher. So this is a perfect deadlock. Before we showed that diagram of those two transactions, it was two nodes with a dependency on each other. So this is a more complex dependency graph, but it's 5 nodes. We could think of this as 5 transactions that have all successfully grabbed a lock on like one of the rows that they need to edit, right? So they all have locks on one row, but now they all need to use a row that another one of them already locked. And so we have 5 transactions all in the circular dependency waiting on each other. And again, the way to break this is Postgres or MySQL would either see that there's a circular dependency in the locks, or they would see that we're going to optimistically let one of these guys pick up the right fork and just kill the other philosopher. Sounds a little dark, but that's how you make progress, right? Generally, the way that you make progress in these things is you need a way to detect it and then kill one of the processes that's trying to use it. You could also just build systems that avoid it, but ultimately that also probably requires ending up killing certain processes, because in order to avoid it happening, you would need to tell processes to stop like requesting resources that they're requesting. So yeah, that is kind of the basics of Deadlock and how it works in databases, and also just kind of some higher level theory on Deadlock. There's interesting, let's see. Yeah, so this is originally proposed by Dijkstra, so it's a pretty famous problem, and then Tony Hoare gave it sort of its present form. But what was the thing that I wanted to, why is there no link to this? Yeah, I'm trying to look at, I guess I just need to go find the other, just go to the Deadlock page. So there are actually, like if you study the theory of Deadlock, there's several official conditions. Like it's not just sort of this made up thing. Like in theory, in the theory of computer science, there's actually official conditions that make up something being considered as deadlock in a system. But kind of what we described is just the colloquial version of that. So that's Deadlock. Interesting. It's something that databases have to think about all the time, and just one more reason why building a database is not an easy task. Someone asked about two-phase locking. I actually wish I understood that better. For some reason, every time I read about two-phase locking, my brain glosses over. But it's talked about in the book. So definitely, and I recommend the book if you want to follow along. Oh, let's see. Someone asked, can you help me understand why I would need a shared lock to read the data? So the reason you would need shared locks to read data is because, let's say you have several transactions, they're all reading data. Let's say maybe there's 5 of them at the same time. So 5 transactions have an S lock on some data. While that's happening, another transaction comes in and wants to modify that. So it's trying to get an X lock, but it has to wait until all of those S locks are released before the X lock can be gained. So the S locks are kind of like a guard that don't allow an X lock to be grabbed until everybody's done reading it, because you don't want those things reading it while there's an X lock, right? Okay, yeah. So select for update is like a way that you can kind of protect rows and sort of do some locking while you're doing queries. Yeah. Transaction fast track. What is the problem? Yeah, I'm not quite sure about this question here. Creating triggers. I'm a little bit confused by this question. Yeah, okay. So we talked about a lot of fun stuff. How long have we been going for? We've been going for a while. Hour 45. Nice stream. At least for me, that's long. For some people, that's short. So anyway, good stream today. Glad you guys could make it. Be posting some of these videos. Thanks for coming. And I hope you all have a great week. I look forward to, and just for those, following along, right? Next chapter is chapter 6, which is actually yet again talking more about B trees, but I think it's interesting because it's B tree variants. So rather than just talking about the standard B tree stuff, it'll talk about different like techniques you can use to modify the B tree structure. Like I read a paper recently on, what was it called? Is it the BF trees, where it's taking a B tree and modifying the way that the buffer cache works with the B tree so that you don't always have to store full pages, but you can store subsets of the data in pages to use your cache more efficiently. So there's a lot of like cool modifications that you can make to B trees to make them more efficient in databases. And so we'll see what is talked about here. My hope is actually to potentially do another stream on Friday. So there may be another one at the end of this week. We'll see. And yeah, Vlad says, I like this book reading series. Yeah, thanks. It's pretty cool. I'm glad you could make it. I'm glad you were able to share it. Maybe we can collaborate on something sometime. There's a thanks, Ben. Yeah, thank you all for coming. We'll see you in the next one and get to reading chapter 6.